Hello, everybody.
Hello, Max.
Who's there?
That's Sean.
G'day, Sean. How are you doing?
Hi, Max. I'm here.
Jules, Guy.
Hi, Max. I'm here. Sean.
How you doing?
All right.
Who else is on?
Job for work.
Oh, okay.
Yeah.
Hi. Right.
And Sam from the Audio Science Forums.
Hello, Sam. Good to talk to you.
Hey, Sam.
Hello, Max. David Sauls, Wire World.
Oh, hi, David. How you doing?
Very
Hey,
good.
David.
Good, good. Yeah, hi. Yeah, this is I suppose you've all read the rather controversial paper. And
Great paper. Love it.
you do? Okay. Thank you. Thank you. Yeah, well, it's I've been aware of this phenomenon since the late 70s, but when this basically this was the cable that started it all, the Polk, which was sold also by Monitor Audio, and this stuff got quite a low impedance, high capacitance, low inductance, and that blew up the name 250, and it was taken off the market. So we came up with this design here, which is the 650 ohm coaxes to give 8.2 ohms. And this is the small one. Then we built a larger one with the heavier duty coax, but that was very laborious. So we went and built our isolder cable, which is, the reason we called it isolder was that big one. There were 900 strands of copper to terminate. We had to split them all out, join them all up, and we had the Rock, the Excalibur, the Grail cartridge, Glastonbury speakers. So it's all Arthurian legends. So we called it isolder because I solder and I solder and I solder, like Tristan and Isolde. So that's how I got the name. And the name is stuck. So what I've got here is the cables that we had. This is the exact same experiment that I documented on the paper. I haven't touched anything. We've got, I've got a little camera here. Can we switch to this camera? Fella? Who's got it? There we are. Okay, so you can see here, there's the various components. We have this is two flat strips you can see there, I guess, joined together. Can I increase that exposure a bit? Let me just see if I can brighten that slightly. Okay, anyway, can you see that? Yeah, there's two flat strips there, which are connected to these two, and this is the other end of the cable, and it's parallel down here. These connectors are the same, these are parallel. And I've made this box just to make it convenient to do this switching. We have here the little Focusrite, the sound card, and that's connected to the computer here. What we're doing, we're being a bit naughty. I'm taking the output, the monitor output here, which is designed to take monitor speakers, which is a 400 ohm source. And that is going over here into the input and selected to go to both cables. And the load is the dummy speaker load selected here, which is, somebody pointed out there wasn't correct impedance curve on the dummy load, and we checked that back and found that yes, that was a dummy load with a Zobel network on it, and we're running the dummy load is the circuit as shown on the drawing, which is actually made. It's inside here. I'm not going to show you in there because it's a bird's nest. It's a nightmare. But effectively, we've got this switch here, which is the main operating switch. Let me just hold still. I can go from there. That is a short circuit, and the short circuit isn't a perfect short circuit because we're working at very low voltage levels here, and the resistance of the wires is getting in the way. But it is a short across the switch, but then the wire resistance upsets. Then this position is a resistor equal to these cables same resistance as the cable. This is the select this pair, and this selects this pair. And if you look at it here, you can see there's one, that is the pair where they're joined together. This is one single run, okay, there. And this is the other single run. So in this instance, they're very close together, high capacitance, low inductance. And here they're low inductance, high capacitance. Right, we can go off that camera now. Oh, go back to this. So what I'll do, has anybody got a question?
400 ohm source, an amplifier is closest to 0 ohm.
But when you match the impedance, it doesn't matter what the source impedance is. It's a current source. And as volts are there, it doesn't matter what the impedance is, but we're not trying to deliver power. We're just trying to deliver volts. And I do have a power amplifier in here, but unfortunately, its frequency response isn't as good as I'd like.
That is totally wrong. You get the same result because you are measuring inductance, not transmission line impedance.
I understand, but and yes, you can say that it's measuring inductance, but the transmission line characteristic impedance tracks almost precisely. And this is the outcome of the experiment, that you've got to, if you get the characteristic impedance of the line and load it with the same load at audio frequencies, you don't get the rise. I'll show you the experiment. Let me do it. You know what the circuit is. Okay, well here we have, this is the crummy short circuit, and you can see the voltage there. We've got about 80 microvolts, and the input is 775 millivolts is going into the line. And if we go through the short circuit equal to the resistance of the cable, you can see that it's relatively flat, which you'd expect. In the settings, you can see 1/6 smoothing. The other settings, so you can see we're 20 hertz to 30 kilohertz. And the micro, it's in volts on the left-hand side, you can see quite clearly, showing in volts. So now if you go to the two flat strips close together, we can see it's virtually identical to the resistor. But then if we go to the two flat strips separated, where the inductance is high and the capacitance is low, there's a big change. Now this, of course, is the voltage across the cable. But I did this experiment initially to show that there are differences in cable by changing the geometry, and this demonstrates that. Now, I can't measure reflections in audio, but I proposed an idea, which you can shoot down or argue till the cows come home, I guess, that every transient is putting in a whole load of reflections, or it may not be. Somebody may be able to prove something completely different. But what is very, very obvious is that the impedance of the load matters in this instance. The characteristic impedance of the cable is the overriding factor. Now, if I've got some other cables here, I can change these two. I'll take that out and put in this.
An audible difference, I think, is the question some have.
It is audible, yes. We've been listening. I wouldn't be doing it if it wasn't audible.
Why not do the null test? I think that'd be the best way to determine that, no?
Which is the null test, the one from Ethan?
I'm not sure. I think I've seen examples where they take the signal from one version versus another and they inverse one and put them together. And if you get
Yeah, well, I've done that on my videos. If you look on YouTube, Geometry Matters, I've done about 5 videos about 12 years ago showing this, where I put it on the oscilloscope and you put one A minus B and look at the difference. and you get a very similar result. But you can see here, that this cable here, you see that the two flat strips are about 1,000 ohms characteristic impedance. This cable here is Van Dam, which is, I think about what is that? Where is it? I can measure the impedance with it.
One question, sorry.
Oh, with a question, sorry, yeah.
You have done absolutely nothing that shows these characteristics of experience and not inductance. I'm quite serious of absolutely nothing. You have made no specific correlation that is characteristic impedance.
Well, I've measured the characteristic impedance, and if I make the characteristic impedance equal to the load impedance, you get a square wave in and a square wave out, and you don't get the rise.
You have done absolutely nothing that shows its characteristic impedance, not inductance. I'm quite serious, absolutely nothing. You have made no definitive correlation that is characteristic impedance.
The comment is that I've made no proof or demonstrated that there's anything to do with characteristic impedance. Some people disagree, and it's just a coincidence that a characteristic impedance defines the shape of the reflection, the rise in the graph, shall we say?
Max, could I
Yeah.
comment?
You
If I own a time delay reflectometer,
Right?
and you know, when I'm looking at the characteristic impedance of cables, it's very predictable at high frequencies, like 1 megahertz. But as you go lower frequency, the characteristic impedance rises. So
Well,
it's very far from linear. So when I talk about this, I just talk about having the Q factor, the inductive Q, as being in the right range to make a cable neutral. And it seems like a simpler and more specific way of saying the same thing you're saying.
Well, it could be. But what I've also found out is if you get the 650 ohm coaxes in parallel, like here, I've got this set here, and if I plug them into the
Oh, I agree. I've repeated that experiment. I know that
Yeah.
works.
yeah,
And
because
so I know it adds up that way. It just, I think from a technical description, the matching and reflection thing, I've not been able to prove in a way that seems to hold up very well in an engineering discussion. Whereas the inductive Q, just calling it that, seems to click more and make more specific sense to engineers.
I can understand that, and it could be that. But see, here is 650 ohm coaxes in parallel. Can you see that screen now?
Yeah, it's like a properly tuned cable now.
Yeah, and that's 650 ohm coaxes. And if I go here, take that out, and put in a 75 ohm coax, which I have here. That one in there.
I really like the way this reflects what we hear. I think this test is beautiful.
Yeah, because it is audible,
Yeah,
but it can get masked.
yeah, like anything. There's some systems with no low-level resolution, and I
Now,
still
see-
don't understand how people can plug in a cable that destroys low-level resolution and like the sound effects.
Oh,
It's
okay,
beyond-
okay. Yeah. Yeah, as Ivor Tiefenbaum said, the wider you open the window, the more the muck flies through.
Right.
But you can see there the 50 ohm coax, the 75 ohm, sorry. On this, that's showing effects in the audio band on white noise.
Sure.
So somebody who's smarter than me, Gunga Din, can probably explain it, but it tracks characteristic impedance quite nicely.
Well, I've been able to measure this a number of different ways, and I like your way a whole lot.
Because the difficulty is, because I first did it with a couple of Android phones, where you take the headphone output and use audio tool with their white noise, and then you use the spectrum analyzer across the cable using a 1 microfarad capacitor to block the DC. And you can get the same graph as we got here. Now,
You know, I started off just using an analog scope and a square wave, and if I just monitor both ends of the cable into a speaker or a dummy load and look at the difference,
yeah,
and
well,
the same thing shows up.
I've got it set up here. I've got it, so here's this 75 ohm coax. I'll put it over here to, can we put this little camera on now? I'll plug that in there. It's a bit ropey, this experiment, because it's been around for about 25 years now. It's starting to wear out. Then in there, that in there, that in there. Right, now, if we look at the scope.
Well, I would invert one, you know, from the one end of the cable. You
Oh
know,
yeah,
to
I've
the
done
other.
that test. But what I'm doing here is I'm just putting square wave in,
Yeah.
and you can see here I've got the pot and I'm adjusting it. Now, if we just, I'll finish this and then I'll have a look at that question. If we adjust it here so there's as good a square wave at each end as we can get, then if I unplug that, and I get the meter here, and plug the meter, oops, got over, turn him on. Oh, damn, stop falling over. Right, now we plug that into here. $75 ohms. So if you get a square wave in, a square wave out, you can find the impedance of a cable, characteristic impedance. And the other one gives 8 ohms.
I've got a question for you.
Yeah.
You've measured the characteristic impedance wrong. Your meter has no ability to control the frequency to measure at audio frequencies, and using a square wave only shows characteristic impedance at high frequencies, which is not the same as characteristic impedance at low frequencies. They are not 8.2 ohms at 20 kilohertz. They're about 24 ohms, and that's from Dan Thomas.
Yes, if it depends on the DC resistance of the cable. The formula is, well, you've got the, assuming it's a perfect conductor, then the current that flows at DC, if you put a current source onto two infinite lines, which is the theory of it, the current drawn is DC with the characteristic impedance. Now, where's the contradiction from that argument to the one with the frequency? Nobody's explained that properly, but I know I've looked at the maths, and yes, the DC component of the cable comes into account at low frequencies. And if you have a look at the paper from Richard Black that's attached to the unit, it gives you the size, the amount of copper you've got to have. But the big thing is, if let's say it is 25 ohms at 20 kilohertz, that means it's far better to be low impedance cable than 1,000 ohms or 800 ohms, which is typical of cables. And this is the point that we're trying to make with the cable design.
And Max, you know, he's kind of saying the same thing I said, is the way you're saying it comes out as somewhat of a technical overstatement, because it's not really a match per se, whereas the Q factor, calling it that, it's kind of beyond reproach at that point, because it is a change in Q factor.
Yeah, well, if it's a change, if that's what's causing it. But all I know is that the cables, there's something really, really magic about matching the cable to the speaker. And I've been doing it now since 1978, 79. And we got product of the year a couple of times. Then again, I suppose quite a few people have with their cables, but just something happens to the sound when you get this right. And it's unmistakable when you hear it.
Right, we've got another question from Dan Thomas, and it is,
Hi, Dan.
if you parallel 6 to 50 ohm cables, it is about 1/10 the inductance of a single 75 ohm coax. Of course, it's going to be less loss at 20 kilohertz.
But if you measure the square wave in and adjust the load, you have to have an 8 ohm load to get a square wave in and out. Yeah. But parallel capacitance adds, oh, sorry.
Okay, we have got a response from Dan, and that is square waves are meaningless at 20 kilohertz.
But there's a DC component on the square wave. Okay, I could accept you can make that argument. Square waves are useless, but we use square waves everywhere when we're designing amplifiers, when we're matching crossovers, phasing speakers to get them time aligned. You use square waves, and you can see it quite clearly that they're aligned.
I think what the other listener was commenting on about is actually in conflict with some of the more recent science on the ear's ability to detect changes in transient response that show a transient sensitivity of the human ear as 5 microseconds. That is 5 millionths of a second. So you are behind the times when it comes to engineering, making a statement like that. That is old science. It has been thoroughly replaced by multiple peer-reviewed papers in the auditory field.
Fortunately, my microphone started working at just the right time, because that argument you just made is colossally flawed. That argument is based on the exact same sound going to both ears, and it measures a timing difference from arrival of one ear to the other ear.
You're talking about one specific paper there.
No, that is exactly what this timing is based on. It is based on the arrival time difference from one ear to the other. It is not based on some fancy transient.
You're not familiar with all the literature.
I am very familiar with the literature. This is what I do for a living. I am very familiar with it because this is what I work. This is the field I work in day and day out and have for 30 years.
You're saying that
audio science
sensitivity was based on time differential between the two ears?
It's based on time differential between. It's time differential. That 5 microseconds is based on time differential between the two ears. That's all.
Still suggests the ear sensitivity to timing is beyond what conventional engineering says.
Conventional engineering makes no differentiation on timing of the earring. All that engineering does is says it looks at frequency response. You can tell the time difference between two ears to microsecond differences at a few hundred hertz. You don't need really highly accurate timing, but we're talking a single speaker source. It doesn't matter if it rise times or anything. All that matters is that the same sound is going from one ear to the other. It's measuring the difference between the two ears in order to tell direction. That's what it's based on. That's all it's based on. And any other, in attempting to make any other correlation or conclusion is.
I'm pulling up a paper right now.
Please do. It is based on time of arrival between the two ears. Look at how they do the measurement. They're looking at time of arrival between the two ears because that's the only way they can do it. They look at how you can tell differentials in timing, and it's based on time of arrival between the processing that happens is time of arrival between the two ears. That's how they do it, because you can't even measure microsecond accuracy from any other arrival factor other than essentially being able to detect positional differences.
Has anybody looked up the James Boyd paper, The Life Above 20 Kilohertz? Where he does the harm and mute, which goes up to at least 100 kilohertz, and jangling keys. And I listened to a lot of hi-fis, and none of them really fooled me into believing that that you've got a real band there. They all seem to be band limited. And I was aware of that many years ago. And I built this little fella, this little super tweeter here, which goes up to 100 kilohertz. And when you're playing high resolution music, 192.24 or good vinyl or even 96.24, and you put this in, you can hear it, difference. But if you disconnect the main speaker and play it, you can't hear anything. But everybody can hear it. I made these in the late 80s, no, in the 90s, not thinking I'd sell any, but we've never stopped selling them. And people are always shocked when they hear the best.
They're introducing harmonics further, into the lower range where it is in the audible range.
There is a little bit. There's a little bit going down at about 8 kilohertz. It's about 60 dB sensitivity at 8 kilohertz. And then it rises to to about 85, 90 dB at around 20 to 25 kilohertz. Now,
But
my hearing,
Max, you made a claim in something you wrote that even with CDs, it made a difference. But
it
CDs
even makes the difference on CD.
CDs don't output anything,
I know
virtually nothing after 20 kilohertz.
But this is rising. The output's rising from about 12
It
kilohertz.
can't rise. Yeah, but it doesn't
the
matter.
sensitivity
Most speakers have flat response to 220 kilohertz approximately. You can't the signal rise time can't exceed the rise time.
No, I understand that, but and I was shocked when it worked on CD. But time and time again, it doesn't matter whether it's a dome speaker, an electrostatic speaker, or a horn speaker, whatever it is. As soon as you put the super tweeters in, well, the hi-fi pigs, they just put them into their horn, their big duos, and they were going to get rid of them because of lack of detail. And they put this in, and it just transformed them. And they go up to 25 kilohertz. Raphael Totis, Allegri String Quartet, he's got quad 62s, and he put them in recently and said, oh my God, it just transforms them. So there's something happening that's not explained by sine wave frequency response listening, which is what usually happens. And I'm not going to argue why they work or how they work, because I'm not an expert, but one of your gentlemen there is.
But let's go back to the cable.
Let's go back to the cable.
You haven't shown causation between characteristic impedance.
Well, it's just a coincidence.
It is actually. It is a
coincidence.
So it is essentially a coincidence, because when you do reduce the inductance of a cable, it'd be very difficult to reduce the inductance of a cable without reducing the characteristic impedance. But we have to look. But look at your experiments. You show the impedance curve of the speaker. If it was characteristic impedance, which you have claimed was right down to DC, but it's not. At DC, the characteristic impedance goes really high. So essentially, if it was characteristic impedance as you're claiming, then you should see bumps in the response that match those bumps in the characteristic impedance, which happen at low frequency. But with inductance, you won't see those bumps because you don't see much losses due to inductance at a few hundred hertz or even a kilohertz. You start seeing them rising up at 20 kilohertz, where it's going to start becoming, where you're going to have at least the noticeable loss. But if it was characteristic impedance and you have those mismatches all along the cable, as the frequency changes, you should see that curve that you did move with the characteristic impedance. It doesn't. It only starts rising up at high frequencies, just like it would with inductance. And I guarantee you'll find a perfect correlation with inductance. You won't find an approximate like you're claiming with characteristic impedance. You'll find an approximate. But even beyond that, just looking at the basic science of impedance matching, it's pretty easy to do a proper simulation. You've got 7 meters. You've got 7 meters of cable. You've got literally hundreds and hundreds of reflections at 20 kilohertz. It'll settle to hundreds, if not thousands of dBs within the final signal. The signal will track perfectly the sine wave. It just will. I'm sorry, this is how transmission lines work.
Yeah,
this is known by we're not talking, we're not creating new science here. People know how transmission lines work very, very, very well. And that's why inductance does parallel transmission line impedance somewhat well until you get to low frequencies, when it doesn't, because the characteristic impedance drops, and it drops quickly. Your 650 ohm cables in parallel aren't 8.2 ohms. They're probably 24, maybe 28 ohms at 20 kilohertz. At 2 kilohertz, they're probably 100 ohms, 120 ohm. But the inductance never changes. The inductance is the same. And
What
that's
about the
why it behaves
capacitance
like
going
an
up?
inductor.
There's a huge rise in capacitance when you lower the inductance.
That
No,
seems like much
capacitance is-
less of a factor because as I adjust that variable, I don't come up with these kinds of changes unless I take the amplifier into an unstable mode. I want to just get back to Dan. Dan, you need to look at a paper by Mylan Kuncher, 2007, which covers exactly what I was talking about specific things that do not have to do with intraoral sensitivity, but have to do with transient changes, and includes references to other papers that actually relate directly to music reproduction, bandwidth, and transient response. So I know you're not aware of that because you claim it doesn't exist, but it's exactly what I said it is.
I'm not
And
claiming it
relates
doesn't
very
exist. I'm claiming the interpretations based on knowledge aren't. I will pull up his paper if I
No,
can.
but I've done specific testing with double-blind listening tests that relate to those specific variables and relate to this inductive Q factor tuning effect in cables. And when we tune the cable to pass the square wave better, and then we compare that cable to a direct connection, as in a monoamp directly connected to a speaker, and then substituting in the speaker cable with a double blind switching system, we can make a cable come much closer to disappearing and not changing.
So what are you matching it to? Where in the impedance curve are you matching it to? 20 kilohertz?
I'm
10
not
kilohertz?
doing impedance matching. I'm
What are you matching
adjusting
then?
parameters into the cable to where it performs better at audio waveforms and passes a blind bypass test.
At what
the
frequency?
best.
At what frequency are you doing it?
I'm not talking about a technical tuning. I'm talking about adjusting the spacing between the conductors until the cable sounds closer to a direct connection, which is what we want.
With which speaker?
We're not looking for I've done it with hundreds of speakers. I've been doing this since 1980.
So you have a different cable for every speaker?
It's no, when the cable's tuned right, it works right on all the speakers.
So it's tuned to the amplifier then?
It's not.
What we found it matters, the speakers vary in impedance. Low frequencies, it doesn't matter because the impedance of the cable is high and the effect isn't down there. The effects start coming in, we reckon, around about 5 kilohertz and up. And that's where the devil's in that fine detail at the higher frequencies. Now, if you make it so that you've got the Zobel network on the end of your cable, which flattens the frequency response of the cable, the Zobel lowers the cable, so it doesn't matter what the speaker does, as long as you're close. But what is happening is you've got huge mismatches where you have 500 ohm cables going into nominal 18 or 20 ohm speakers. And by making the argument that it should track the impedance curve of the speaker, that's like saying, and you're not matching, it's like saying, well, a car has got a good, in first gear, it's optimum, but at 3,000 revs, but we go from 1,000 to 5,000 revs where it's suboptimum. So because it's not optimally matched all the way through, drive everywhere in overdrive.
No, that's not what I'm saying. I'm saying that, for one, most people who make reasonable quality cables don't make ultra high inductance cables because it doesn't make sense, because it rolls off the high frequency. There are some who do it intentionally because, let's face it, some people like that sound. But you're still not showing anything but inductance. And even a tuning, you're talking about tuning, but you're not doing any actual measurements to show what you're tuning. So you essentially have no idea what you're tuning.
Well, you're really misquoting again and again here.
Well,
Dan.
no, what you told me you did do, but I asked you, what did you tune to?
No,
we tuned it by sound.
I'm telling you, when I passed the square wave in the audio frequency range with the least differential, that's pretty much the same.
And I asked you what frequency you did it at, and you didn't
Well,
tell me.
I've run through, I mean, commonly with a speaker cable, I've had good results at a 5 or 10 kilohertz square wave. 5 kilohertz is enough.
Okay, so the impedance of the obviously of the speaker changes to 5 and 10 kilohertz. So you match. That's why I asked. Oh, you matched it per speaker? No, it works for all speakers. Make up your mind. It can't work for all speakers and then do 10 kilohertz.
What I'm saying, I can take a load and a cable, and run a square wave through it and look at how that square wave changes. And when I adjust the parameters of the cable for minimum change, and then I run through the same procedure with a listening test, direct versus cable, that the two match up very closely, almost identical to the same result.
Again, I'll ask, you said you did a tuning with a square wave. What did you tune it to? A load, a dummy load, right? How is a dummy load like a speaker?
Are you just looking for reasons to say
I'm just pointing out the lack of consistency in your argument.
It's not a technical argument. I'm trying to make a cable sound like a direct connection. The fact
but you don't know, but what I'm saying is I'm not even arguing that you're not tuning it. But for all I know, and you say it works for everything, for all I know, you're tuning it to the behavior of a crossover, because that actually can make a difference. You can actually tune a cable to not get a wiggle at a crossover. You can actually improve the transient response at a crossover with a cable. And that may be all you're tuning, and it has nothing to do with these high frequency effects you're trying to claim.
Yeah, but we don't.
And on that note, David,
because and I say this because you don't know what you tune. You can't tell me what you tune to. Well, it works for all amplifiers, all speakers.
David, if you have the documents,
tune a cable that way.
If we have any documents that you wanted to share in the chat, which you can bring up by pressing the chat thing, that might be a little bit of a better way to go. We're getting slightly.
I'll turn it over to other people, because
no. If there is scientific evidence,
there's lots of scientific evidence for all this stuff.
So yeah, you can share that in the chat, and we can go back to that. So we're going to cut back to Max quickly to just to stay on track here. But yeah, do get familiar with the chat. If you press the chat thing at the bottom of the screen, you can share documents. We can cross-reference documents together, and we can all go over it, and we're all singing from the same hymn sheet, so to speak. So we're going to hit back to Max now.
Anyway, just to summarize, what we do is we make it so that the impedance at the speaker is around 10 ohms. That seems to be a pretty optimum position. And the cables, if you measure them with the square wave and then you measure what the impedance is, it's about 10 ohms. And that's how we've arrived at this. Now, yes, you can argue it's nothing to do with the characteristic impedance, it's just a total coincidence. Well, I'll settle for that, but believe me, as a square wave in and a square wave out is the answer. And if you don't get it, then it just doesn't sound right. And the funny thing is, with this matching the cables, when you have a mismatch, it gives a roll off, which I've measured, and you can see it's rolling off at high frequencies. But mismatched cables sound bright. They sound awfully bright. And you can walk past a room at a hi-fi show, and I can hear the cables in the hall. I say, oh my God, I bet those conductors are about 1.5 inches, 2 inches apart. And lo and behold, they are. It tracks. And it sounds brighter and blurry. Whereas when it's matched, it's clear and like real life. So that's the listening experience I've had, and I think there's a lot of other people have had a very similar listening experience. So I think the jury's out. We're going to argue about characteristic impedance. It's a total coincidence. Some good engineers say that it's nothing to do with it. Some good engineers say it does. So what can I say other than thanks very much for listening. And if anybody wants me to do any more little tests here, I'm more than happy to.
Max,
yeah,
can we hear the difference between cables? Can you show us an audible sound?
I can put the amplifier in. I've got only trouble is it's not my best audio effort ever.
I think we should sort of brace ourselves that we are just using through Zoom, so we might not get any audio file revelations here, but maybe we'll hear a difference.
Let me put in.
I ask because having heard the experiment firsthand and having heard the difference, I was just hoping it might be able to be apparent to other people.
That's the short circuit. Can you hear that? Can anybody hear that? That's coming through?
I can hear that.
If you can turn on original sound on your Zoom, then we won't get any of the DSP. So if we can do that, we've got a bigger chance that we might actually hear.
Well, here it is. That's the short, very little. That's the resistor equal to one run of the cable. That's the isolder, and that's the split cable. That's the two separate runs.
That's a very clear difference this end.
Yeah, that's
Yeah.
obvious,
Yeah,
Max.
too, as well. Yeah, very clear.
Yeah.
You can all hear that, Max.
Yeah.
So there's obviously something happening in the system that does prove your point.
Yeah. But the funny thing is, that is a loss in the cable. It's an increase in loss. But when you listen to the cables, they sound brighter and blurred.
You know, Max, I have an alternative explanation here that's a very good fit. And that is that the inductance increases the duration of high frequency transients. And of course, we all know that as you increase the duration of a transient, we increase its apparent volume. This is following standard psychoacoustic theory. We don't need to measure reflections or oscillation or anything to understand this. That's a very well documented effect.
And the other thing is that with this, the little super tweeter that goes right up high, the precedence effect takes over, because you don't have to turn off your main tweeters to hear what the super tweeter is doing, even if it's at lower level.
Yeah.
Comes through because the ear latches onto the first arrival time, and anything that arrives within about 3 or 4 microseconds after that is ignored by the ear, which is bizarre.
But as we add inductance, according to standard theory, we can increase the duration of a transient.
And as you add inductance, you lower the capacitance, and that's the seesaw effect. And calling it transmission lines, it's just a coincidence.
Right. So, I mean, I think my explanation is the straightest, actually, for exactly the same effect that you're demonstrating.
Right. Well, we found the same thing, which is there is a difference. And a lot of people say there's no difference in cables. You can't hear any difference. That's what I set out to do in the first place. And I came out with this link that is pretty tight. And every time I do it and measure, it's very, very close. So it's a bit like, you know, the sun rises every morning and sets every evening. Maybe the earth is round, but that is probably, I could be totally wrong here, but there is a total exact correlation. And that's what I set out to show. Okay, any more questions?
I just want everybody to know that when we do an actual listening test of cable versus no cable, we basically prove everything you're saying.
Which I would exactly expect.
Yeah. And if anybody wants to do those tests, I've been studying double-blind audio tests for a long time. They're actually very difficult, but I've come up with a protocol that's given me much better results than the others. And it's actually mathematically the simplest also. It's called a triangle test. And all you need to prove something with a triangle test are 6 sequences with 3 samples in each test. And this best listening test for cables, you know, again, there needs to be a reference. There can't just be one cable versus another cable. So no cable is the reference. And within each group of 3, the listener needs to pick out the one degraded sample, because the other 2 samples are reference. This has given me much better sensitivity than the other tests. And we have people pass this test regularly. But the idea that the average person could pass is really wrong. These are, you know, very good listeners that are able to pick out a cable consistently. And this style of test, a triangle, only requires 5 out of 6 correct answers to basically prove that something is audible.
Yeah, and there's an old saying that I heard many, many years ago, that if you can measure it on a scope, that something's wrong in the audio band, you can hear it.
Dave, do you have a YouTube channel with any of this stuff that we can look at?
No, I make recommendations on my website. I make, you know, I have the discussion in the technical section of what my recommendations are. We've got some recorded samples, you know, using again cable versus direct. We're not, we haven't put any of those up at this point. You know, they're cable losses. They're not huge. You need a really good reference situation and a good listener. If anybody follows what it takes to do a proper double-blind test in the real world, there's nothing simple about fine audio differences showing up in these tests. I use the MPEG group's literature and others to get where I've gotten, but still listener training, very good playback system, all these things are requirements.
Has anybody got any more questions? Or
I'd just like to say, Max, that we're all listening to you on Zoom, which is not exactly audiophile standard, and we all clearly heard the differences that you're able to show us using your machine. I think that's remarkable.
thank you.
Yeah, thank you so much, Max. It's wonderful.
Okay, it's a pleasure, and thanks guys for listening. And I hope it's cleared a few things up that, yeah, I ain't perfect, but at least I'm having a go.
Terrific. We appreciate it. Love your turntable too.
Oh, thank you very much. Yeah. Yeah, I got to make another one now. Popular demand.
Yeah, very good.
Yeah, we just got a couple of nice prizes for our preamp as well.
Excellent.
Product of the year twice, which isn't bad. Yeah, so thanks very much.